Let's start off with our fourth session on Module 5, Analog Circuits. Good afternoon. Uh, the outcomes of today's class would be to analyze and design the circuit of a half-wave precision rectifier, to understand the working of half-wave and full-wave precision rectifier, and if time permits, we'll move on to understand the basics of active filters. And in that, let's study the working of low pass filter. First, let's study the behavior of the four types of filters, their frequency response characteristics, and then let's move on to low pass. So, next topic, that is precision rectifiers. The questions asked can be something like this. Explain with a neat circuit diagram the working of a small signal half-wave precision rectifier using an op-amp. And as I was telling you in the first class, in our first class on rectifiers, what is the problem with an ordinary rectifier? An ordinary diode rectifier, though it rectifies the input sine wave to a half sinusoid, it's going to convert it, but whatever peak voltage I have for the input, coming to a regular rectifier, a diode based rectifier, half wave rectifier, we always have this diode conducting only when the input signal V in here should cross the cut-in voltage of the diode, which will be around 0.7 volts. Only when the input voltage exceeds 0.7 volts, then you can rectify or the diode will start conducting. And the output voltage, the output half wave voltage will always be less than the input peak voltage by a value of 0.7 volts, because the drop across the diode should get subtracted, as you can see. So, if I have input signals whose amplitude is much lesser than 0.7 volts, say I have input signals in the millivolts range, I want to rectify 10 millivolt signal or 100 millivolt signal, then it's not possible for me to work with an ordinary diode rectifier, but I will replace this diode with something known as a precision diode. If I replace the ordinary diode with a precision diode, then I can work with input signal levels which are in millivolts. Say I'll have peak to peak 100 millivolt signal. I can rectify even this signal, okay, which is in millivolts, if I make use of an input signal which is less than 0.7 volts also. So hence we need to use a precision rectifier or a precision diode based rectifier. And how do I design this precision diode? I have to make use of an op-amp and connect the diode within the feedback loop of the op-amp. So if you connect a diode in the feedback loop of the op-amp, you will be able to make it work with much higher precision. Or when I say higher precision, I'll be able to overcome this cut-in voltage of 0.7 volts, which is needed by an ordinary diode. So when an ordinary diode is used, we needed a cut-in voltage of 0.7 volts and we needed the input to be more than 0.7 volts, right? But when we are using this diode within the feedback loop of the op-amp, what do you think will happen? You see in this circuit, the diode is connected inside the feedback loop of an op-amp. So this cut-in voltage V gamma for this conducting diode will get divided by the open loop gain of the op-amp. So V gamma gets divided by the open loop gain of the op-amp, and that is the new value of cut-in voltage of this diode. Hence, this circuit this whole circuit where I'll connect a diode within the feedback loop of an op-amp is called as a precision diode. This is a precision diode, and the simple reason why it is called a precision diode is because it will have a very low cut-in voltage. That zero point 0.7 volts drop which was needed for an ordinary diode rectifier to conduct is not needed here. So here, even if I give an input signal as small as 10 or 100 millivolts, I can even rectify that signal. You see here we have given an input signal between minus 100 millivolts and plus 100 millivolts. We are able to rectify even this signal in this case. Okay. Hence, this is the behavior of a precision rectifier or a precision diode circuit. Okay. So you will have the output voltage around V gamma times less than the input, and will not have the rectification action until the input voltage is more than 0.6 or 0.7 volts for a silicon diode. So we can't have the ideal diode behavior. Now, if at all we want to rectify input voltages which are less than 0.6 or 0.7 volts, what should we do? I should make this diode behave something similar to that of an ideal diode. And when will a diode behave similar to that of an ideal diode? When I convert it to a precision diode. So I'm going to convert the normal diode to a precision diode. And how do I do that? If I have to convert this normal diode to a precision diode, I will just include this diode in the feedback loop of the op-amp. See, I am going to connect an input signal here, and I am going to connect this diode within the feedback loop of the op-amp, and I'll measure the output here. What happens when we do that? So whenever we include the diode in the feedback loop of an op-amp, its cut-in voltage, the cut-in voltage V gamma, which is 0.6 or 0.7 volts, which we had for a diode, it will reduce by the open loop gain of the op-amp. Remember, the open loop gain of the op-amp is in the range of 10 to the power of 5. Therefore, this cut-in voltage 0.6 or 0.7 gets divided by the open loop gain of the op-amp, and any input voltage when it is greater than this voltage level. So the input voltage which is given here, if it is just greater than 0.6 by 10 to the power of 5, then this diode will start conducting. We don't need the diode drop to be exceeded by the input signal. The input signal should exceed the diode drop divided by the open loop gain, which is, this will be in microvolt. So when the input signal is few microvolts also, this diode will start conducting, provided positive input is given to the non-inverting terminal. So ideally, this whole setup, as I was telling you, this complete setup behaves like a precision diode. So we spoke of a precision diode. A precision diode is something similar to an ideal diode. So the whole setup here works like an ideal diode or a precision diode. The word precision there means high accuracy. I am able to rectify very low input voltages which are in microvolt range. If you are able to do that, you call it as a precision diode. So let's see how this precision diode can be used to help design the circuit to work like a half wave rectifier, and we also call it as small signal half wave rectifier. So when I say small signal, remember the voltage levels are usually less than what? Plus or minus 10% of the Q point levels. So we have the Q point voltage say VCEQ or ICQ, voltage levels we are talking are less than plus or minus 10 volts, 10% of the Q point voltage level, which we will fix. Then we call it as small signal. And remember here, when I say small signal, we are normally working in millivolts or microvolts range. So we are working with input signals which are in few milli or microvolts. Okay. So as I was telling you, conventional rectifiers can rectify AC voltage whose amplitude is more than the cut-in voltage of the diode. Whereas by using a precision rectifier, it's possible for us to rectify very small AC voltages. So let's see, it's the same circuit what I drew there. This is the circuit of a precision diode, an op-amp, and a diode present in the feedback loop of this op-amp. So the input signal is given to the non-inverting terminal of the op-amp, and this diode negative or cathode of the diode is connected to the inverting terminal to complete the negative feedback loop. Okay, so let's try to analyze the working. How does this work? We have given input voltages Vin of around 100 millivolts, let me say, peak, one peak. So 200 millivolts peak to peak or 100 millivolts peak. You can see here in the waveform. So what happens now? When Vin is in its positive half cycle, whenever Vin is going towards its positive half cycle, it is increasing like this. As soon as it exceeds 0, so as soon as Vin exceeds 0 and becomes positive, what will happen? This op-amp will be in open loop condition initially because this diode will not be conducting. So when it's in open loop, whatever small voltage, positive voltage which we have, that will get magnified by a factor of 10 to the power of 5, which represents the open loop gain of the op-amp. Okay. So whatever input voltage we give here, maybe few millivolts of input voltage will get amplified by a factor 10 to the power of 5. So I'm going to have a large positive voltage at this point. Let me call this as VOA. VOA becomes positive and it is a large value. Okay, it tries to be a large value, a high positive voltage. Why this happens? Because initially D is off. Initially, the diode is off. So as soon as the input starts increasing and this becomes positive, now we know this negative cathode is connected to the negative terminal. So naturally, diode switches on. Now diode switches on. Once the diode is on, it will form a closed loop connecting to the feedback loop, connecting to this inverting terminal. So what does this circuit look like now? See, this circuit looks like, what circuit is this? It's a closed loop and I'm measuring the output voltage here, V0, and the input is given here. What does it resemble? This is the circuit of a voltage follower. So this is the circuit of a voltage follower. Now when this diode is in conducting mode, this acts like a closed switch. The diode acts like a closed switch and the circuit looks like that of a voltage follower, allowing the output voltage to follow the input voltage. So whatever input voltage we have given here, you can see the output voltage will follow the input voltage, and you can observe clearly if the input voltage has a peak value of 100 millivolts, the output will also have a peak value of 100. It won't be less, for the simple reason that as soon as the input has started going above 0, this circuit has the diode conducting and the feedback loop is closed and the circuit works like a voltage follower. So the output voltage will simply start following the input voltage during positive half cycle of the what? Input signal. During the positive half cycle of the input signal, the circuit diode switches on, circuit acts as voltage follower. Therefore, output voltage will follow V in the positive half cycle. Okay. And coming to negative half cycle, what happens during negative half cycle? In the negative half cycle of input, you can see in this waveform. So as soon as this input voltage starts going negative here, so the input voltage has started becoming negative, V in. So here V in becomes less than 0. What do you think will happen in this circuit? As soon as V in becomes less than 0, you have a voltage which is negative at the non-inverting terminal. So naturally, it gets amplified by a factor of the open loop gain 10 power 5. You will have something closer to minus VSAT here whenever this op-amp is in open loop mode. And remember, initially, as long as this diode is not conducting, the op-amp will be in open loop mode. This output of the op-amp will move towards minus VSAT. Here, output move towards positive saturation plus VSAT when we give a positive input signal. But whenever I give a negative input signal, you see the output will move towards negative saturation. So when Vin becomes less than 0, initially when D is not conducting, so whenever this diode is not conducting, what happens? The output of the op-amp move towards negative saturation. Remember, comparators we have studied in module 4, which tells us the output voltages which are possible in an open loop op-amp are either positive saturation or negative saturation. We have discussed that. So here the op-amp output will move towards negative saturation. Now, what will happen to this diode then? Remember, there is a diode here with a large negative voltage at its anode, and the cathode is connected here. So this cathode voltage will almost be same as this input voltage. Okay. We remember the principle of virtual short. So what you can surely see is this diode will now be reverse biased. I have a higher voltage at the anode and a lesser voltage at the cathode. So diode becomes reverse biased, or it will not conduct. It will switch off. The diode will be switched off in this circuit. Now what happens when the diode is switched off? How will the circuit look? The circuit looks, you have an open circuit here because the diode is off. Remember, a diode that is switched off will not allow any current to pass through it. So this will be open. So what will be the final output voltage across the load? Diode is off means the output voltage across the load will be 0. I don't have any current. Only when this is a closed loop, it behaves like a voltage follower, and the output voltage will follow the input voltage as we saw, right? But here, since the diode is switched off, the output voltage will be 0. V0 turns out to be 0. And you have observed the same thing in the waveform. During negative half of the input, the output tends to remain 0. During positive half, output follows the input, and during negative half of the input cycle, when the diode is off, the output remains 0. Is this clear? So we have this circuit where a diode is connected in the feedback loop of the op-amp, working like a precision diode, where for very low input voltage levels also, the output will be obtained and I can easily get a rectified output which will clearly follow the input signal. I don't have any difference in the amplitudes of the input and the output. Both are equal because this circuit will divide the cut-in voltage of the diode by the open loop gain. So we see the cut-in voltage V gamma gets divided by the open loop gain of the op-amp, which is very large. Hence, it can rectify signals which are in microvolts also. Okay, so easily in millivolts. I hope all of you understood the working of a half-wave precision rectifier. Now, if I try to draw the transfer characteristics for this, what do you mean by transfer characteristics? Transfer characteristic is a plot of what? Output versus input. So transfer characteristics will be a plot of output versus input. Let me write the generalized equation for output. The generalized equation for V naught will be something like this. V naught will be equal to Vi for V in greater than 0 and it will be equal to 0 for V in less than 0, right? This is nothing but positive half cycle of the input signal. This is negative half cycle of the input. So I can write a standard equation in this form for the behavior of the half-wave precision rectifier which we have considered. Now if I try to plot the output versus input, what would you get? V in versus V naught. This is directly following from the waveform. When input is in its positive half cycle, output follows it. It will be equal. When input is in negative half cycle, output is 0. So positive half cycle means as input is increasing, output will also increase. When input is 0, output is 0. When it is 1 volt or 1 millivolt, this will also be 1 milli. If it is 10 millivolts, it will be 10 milli. If it is 100. So what do you observe? You will get a straight line like this in the first quadrant with slope 1. Output follows input. Therefore, slope of this line is 1. This is called the transfer characteristics for the output-input relation in the half-wave precision rectifier which we have considered. And we should also continue this for negative inputs. So for positive input, we know output follows the input. What will happen when the input is negative? Negative input means I have to move in this direction. Output remains 0. So for negative input values, V naught remains 0 whenever V in is negative. We saw for V in less than 0, output remains 0. For V in greater than 0, output follows the input. So you will see transfer characteristics looking something like this. Is that clear? So this is about the half-wave precision rectifier and its transfer characteristics. What do you think will happen if I reverse the diode? Anybody? If I reverse the direction of the diode here, what will happen? Very simple.
It would work for the negative half cycle.
Exactly. It would work for negative half cycle of the input. So if you just reverse the diode there, you will see that this diode will start conducting when the input goes negative, because a negative value at the input side will make the op-amp output go towards negative saturation, and this diode will be switched on during negative half cycle. So what you will see will happen is these negative half cycles will get converted to positive half cycles, and during positive half cycles this diode will be off. So I'll have zero output during positive half cycles, and I'll have positive output during negative half cycles of the input. So this is the situation when diode is reversed. Okay. And the transfer characteristics also, if you see, you will get it in which quadrant? You will get the transfer characteristic in the second quadrant. Negative input minus V in positive output. For positive input, output is 0. So you will see the transfer characteristics will look like this if you just reverse the diode. So remember this. It's very easy to understand the behavior of these precision rectifiers. Now, usually there is one small problem when I make use of a single diode in the feedback loop. Do you know what that problem is? As I told you, whenever this diode is not conducting, the output of the op-amp will be in one of the saturation levels. And it becomes very difficult, or a larger time is needed for the output to shift from. So this VOA, what happens? What happens to VOA? At some point, VOA will be at a positive saturation. When it is at positive saturation, the diode conducts. What is the drop across a conducting diode? It is 0.6 or 0.7 volts, right? So whenever the diode conducts, the output of the op-amp will be at 0.6 volts. The drop across this plus 0.6. But whenever it is not conducting, so positive half cycle, it will be like this. For negative half cycle of Vi, what happens? The output of the op-amp goes to minus Vsat. When it goes to minus Vsat, that's when this diode stops conducting, or it becomes an open circuit. So what is happening at this output VOA? VOA has to change from plus 0.6 to minus Vsat, and back from minus Vsat to plus 0.6 for every half cycle of the input. So whenever the input goes to positive half cycle, the output of the op-amp, which was at minus Vsat, will have to shift to plus 0.6 volts, or a positive value. And whenever it is going from positive to negative half cycle, it should change, the drop would change from 0.6 to minus Vsat. So since it involves a huge change in the voltage level, the time taken for that change will also be higher. So the time taken for output of the op-amp to change from a saturation level to the other level of 0.6 or something will take much larger than if the change had to be between smaller voltage levels. For that, what we will normally do when we design a practical circuit is, I will include another additional diode. So practical precision half wave rectifier will make use of another additional diode, which you can see here. This is the additional diode which is connected in the feedback loop. So what is the purpose of this diode? What is the use of this diode? The output of the op-amp, which I said VOA, will be at what? VOA will be at plus 0.6 volts when D2 is conducting. So whenever this diode D2, which is there in the feedback loop, whenever this is on, the output will be at what is the drop across the conducting diode? Plus 0.6 volts. So output will remain at plus 0.6 volts whenever D2 is conducting. But whenever D2 is off, what happens when this is off? You see this diode is connected in the other polarity. In the sense, negative of the diode D1 is connected to the output of the op-amp, where positive of D2 was connected. So naturally you can guess, if D2 is off, D1 will surely be on. D1 turns on. Okay. So whenever diode D2 will be off, when will this happen? When VOA tends to go towards minus VSAT. And when will VOA go towards minus VSAT? Whenever the input was given here. In this case, we have changed the position. Input is also given to the inverting terminal. So you will see it is a little more interesting how the waveform will change. Okay. So for now, I will talk in terms of just VOA. Whenever the output is at minus VSAT, diode D2 is off and D1 is on. So whenever D1 is on, what will happen as soon as this diode turns on? The drop across this diode will be 0.6 and the output of the op-amp VOA is connected to the negative end of 0.6. So VOA will be minus 0.6 volts. So can you see the beauty of this? When VOA was positive, the output tended towards positive saturation and D2 was conducting. And whenever D2 was conducting, D1 will be switched off. Okay. So whenever D2 was conducting, if D2 is conducting, D1 is surely off. Both the diodes are connected in opposite polarities. Whereas positive of D2 is connected to the output of the op-amp, negative of D1 is connected to the output. So when D2 is on, D1 is off, then the voltage across this conducting diode, which is 0.6 volts plus 0.6, output will reach that value. VOA tends to be plus 0.6 volts. But whenever this D2 is off and D1 is on, you see that the output of the op-amp will be at minus 0.6 volts. So what will happen at any point of time? At any point of time, the output tends to switch between. So if I try to plot VOA, you will observe. Yeah, I am repeating. VOA, if you are going to observe, it will change between just minus 0.6 to plus 0.6, minus 0.6 to plus 0.6. This will be the output of the op-amp. Whereas previously, how would the output change? In the previous circuit, the output of the op-amp, if I try to plot VOA, this would remain at plus 0.6 volts here, and here it would reach minus VSAT. Okay. And again, when it comes to the positive half cycle, the output will retain the voltage value plus 0.6. In the negative half cycle, so there is a huge change happening in the output of the op-amp in the previous circuit. And that large change causes a timing delay. Remember, though we expect the output to follow input very quickly, that doesn't happen. There is always some fixed slew rate. I told slew rate is the reason for output becoming slower than the input. So every op-amp has or needs a sufficient amount of time to make the output change by a large value. If the output has to change by a smaller value, then it would be faster. Here the output should change between minus 0.6 to plus 0.6. That is because of the use of a second diode. Whereas in the first case, it had to change between plus 0.6 to minus VSAT. Okay, so just repeating this quickly. What happens in a practical precision half-wave rectifier? We are going to include one additional diode, and here we have also shifted the input signal to the inverting terminal. So let's try to analyze the working of this circuit. You will understand how it works. So working of this circuit, when the input is positive, input is in its positive half cycle, what would the output tend to be? See, I have a positive input given to the inverting terminal. So initially you always consider op amp will be in open loop. So what will happen to VOA? VOA will try to move towards minus Vsat. Yes or no? Whenever I give a positive value at the inverting terminal, remember inverting configuration of op amp will invert the output. Positive at the input, I should get negative at the output. Negative means it will be moving towards minus Vsat. But as soon as this value here, as soon as VOA crosses minus zero point 0.6 volts. So when the voltage here becomes greater than minus zero point 0.6, diode D1 starts conducting now. See here, you can see D1 is connected with the negative at the output. So when the negative voltage here exceeds minus zero point 0.6, D1 will start conducting because it has sufficient voltage. And since there is a negative voltage at the anode of D2, D2 is off. Clear? So initially, when I give a positive value at the inverting terminal as V in, so whenever Vi is greater than 0, output will move towards negative saturation, but it won't go till saturation. As soon as the output voltage crosses minus zero point 0.6 volts, this diode will conduct. It will become a short circuit and this diode will be an open circuit. So can you tell me what will happen to the output voltage now? This is shorted, this is open. So will I have any current in this output circuit? Since there is an open circuit here, no connection here means the output voltage will be 0. Please understand that. The output voltage always depends on this diode D2. Okay. This diode D1 is only for the reason of avoiding delays of output reaching negative saturation or positive when the diode was in, avoiding delays due to output reaching saturation. But the diode D2 being on decides whether output should be there, and when it is off, there is no output. So once there is an open circuit in the feedback loop, output will be 0. Please understand that. So you can observe the waveform here. During positive half cycle of the input, you see the output is 0. And during this time, D1 diode is on and D2 is off. Okay. So here V0 becomes 0. That's what we have shown. Next. So this is case 1. What happens in case 2? When Vi is becoming negative. So what happens when Vi becomes negative? Whenever the input voltage becomes less than 0 in this circuit, so I have a negative voltage here. I should get an output which moves towards positive value because of inverting. Since the input is given to the inverting terminal, the output voltage tends towards plus Vsat for negative input voltage. So what happens then? VOA will try to move. Remember, this is only try to move towards plus Vsat. Here also, just tries towards minus Vsat, but it will stop at minus 0.6. Here, as soon as this becomes more positive than plus 0.6 volts, which is the cut-in voltage of this diode, D2 will start conducting now. So, as soon as VOA exceeds plus zero point 0.6 volts, D2 is on. And remember, whenever D2 is on, naturally D1 will be off because D1 is connected with cathode to this output. So D2 is on and D1 is off. Now, how would the equivalent circuit look like? The equivalent circuit, if you observe, will look something like this. Let me draw it here. It will look like I have an input signal here. You observe, you have the input signal given through a 10K resistor. Okay, I hope you are able to see here. Input given through a 10K resistor, and I have another 10K resistor here, and I have this diode D2 on. D2 is on, which is connected to the output of the op-amp, and the other diode D1 is off. So there is an open circuit here and closed circuit here. And if you have any load resistance here, you can easily say what would the output be. Yes, this is an inverting what? Inverting amplifier. What is the output of the inverting amplifier? The output of the inverting amplifier is minus RF by R into VI. What is the value of minus RF in this circuit? Minus RF is also 10K, R1 is also 10K. So minus RF by R1 into VI. Both are 10K, so minus 10K by 10K into VI is also a negative value. So what will I get? I'm going to get the output as following the input, but with a positive sign. You had given negative input in this half cycle, but for a negative input, I'm going to get a positive output here. And I hope you understood the reason for that. You see, the circuit of the op-amp resembles that of an inverting amplifier. And in an inverting amplifier, we know the output is negation of the input with gain minus RF by R1. I'm not giving any gain in this circuit. I have used equal resistors. So the output will follow the input but with a negative sign. You see, when the input is negative, the output becomes positive in this half cycle. And in this half cycle, you should remember diode D2 is on and D1 is off. Is this clear? This is about the working of a practical. Can somebody draw the transfer characteristics for this behavior? Your output behavior changes according to where you have connected the input. Here, input is connected to the inverting terminal of the op-amp. You always have an inverted behavior. That is, I'm going to get the negative half rectified to positive half cycles at the output. What if I wanted the reverse? Positive half cycles becoming negative half cycles and rectified. What should you do? Yes? Same as before. If you want the positive half cycles to become rectified to negative half cycles, you just have to reverse both the diodes. You reverse the direction of both the diodes, your positive half cycles will become negative half cycles. Okay? And let's draw the transfer characteristics here. I want you to understand how the transfer characteristics looks. Okay. This is V0 versus Vi. This is negative Vi and this is positive Vi, and this is positive V0 and this is negative V0. So you can observe what is happening initially in for Vi. When Vi is going positive, the output remains 0. So if I try to plot the output voltage, say for positive half cycle, it should remain 0. It will be on this axis, correct? Whenever the input is positive, the output is 0. You can observe. You can write the equation also like how we wrote in the previous case. And when the input is negative, that means on this axis, what is happening to the output? Output is becoming positive. So it will be something like this. You see, whenever the input is negative, the output is becoming positive. Hence, I'm going to get this transfer characteristics to look something like this. Whereas, if I interchange the diodes, what would happen? You can easily guess. If you have this diode in this direction and this diode also in the opposite direction, and as usual you have a 10k resistor here, a 10k here, and the input signal given here, the non-inverting terminal can be grounded through a compensation resistor, right? You can have a load resistor here. What happens in this case? You will see, for when I told you, you will get an output only when this diode is on, D2. When do you think D2 will be on? When I get a negative voltage here. It's very simple to analyze. You need not worry much. You will have the output voltage present only when D2 is on. You have to analyze what is the condition for D2 to be on. If D2 has to be on, I should get a negative voltage here, a high negative voltage, or this VOA should tend towards minus Vsat. When will this become negative? When you give a positive input. So whenever you give a positive input, output will move towards negative because the input is given to the inverting terminal. Yes or no? So since you're giving the input to the inverting terminal, the output tends to become minus Vsat. But as soon as the output voltage here exceeds minus 0.6 volts, we have 0.6 voltage drop across this diode. So as soon as that voltage is exceeded, this diode is conducting and output will follow the input but with a negative sign. Output will now be equal to minus of Vi. I have given a positive Vi, but I'm going to get a negative output. And that is during positive half cycle. So if I try to draw this waveform here for this condition, whenever the input is positive, the output will be negative and it is present. Okay, it will, I can't draw it to the same scale, but imagine it will be same when diodes are reversed. When diodes are reversed. Okay, and what happens next? So when this diode is on, this will be off. For the next condition, when I give a negative input, when input becomes less than 0, I have a negative input, this becomes positive, it moves towards plus Vsat, which means this diode will be off, this diode will be on. Open loop here means the output becomes 0. So what you can see here is the output will be 0 for negative input, but it will be a negative value equal to the input in magnitude. So you'll have the same Vm for positive amplitude. So can you tell me how will the transfer characteristic look for this? What would be the transfer characteristics for this condition when both diodes are reversed? Input is positive, this side, right, plus Vi. Output tends to be negative. So it will come in the fourth quadrant, exactly opposite what you got here. You got the transfer characteristic straight line with slope 1 in the second quadrant for this circuit. It will be in the fourth quadrant when both diodes are reversed. So as soon as you see this, you should be able to analyze. Is this clear for you? If you have any doubts, please ask. So normally in a practical circuit, we'll use one additional diode to prevent what? To prevent the output to take a long time varying between minus Vsat to plus 0.6 or something like that. So if I want to have a smaller voltage change, the transition at the output VOA will happen faster. That's the main reason why we use this diode D1. Is that clear? So even without D1, it still works. If you use a single diode also, like how we saw in this first circuit, it still works. Only reason is the time taken is longer. Okay. So this is about the various half-wave precision rectifiers and the advantages of half-wave precision rectifiers over a simple diode rectifier would be no diode drop between the input and output. That means if the input is 100 millivolts, the output peak will also be 100 milli. I'll not get it as Vm minus zero point 0.6. The diode drop will lessen the output in a normal rectifier. It won't happen like that in the precision rectifier. I already told you that. And its ability to rectify very small voltages is another advantage. Amplification is also possible if I consider this circuit. Here I have taken RF equal to R1 because I didn't want any amplification. But if I want a gain of 5 or something, I can make RF 5 times R1, it still works. So whenever the input is in its negative half cycle, I'll get the output to be 5 times the input value. You can amplify as well as rectify. Even that advantage we have in this circuit, in the practical circuit. And it has a low output impedance, which is a great advantage. We know any circuit should have high input impedance and low output impedance. In the first circuit where I have given input to the non-inverting terminal, the input impedance will also be high. Remember, we already derived in module 4. For a non-inverting amplifier, it has a very high input impedance and low output impedance. So that condition is satisfied in this precision rectifier. But coming to this one, since we are using an inverting amplifier, here the input resistance will be equal to R1. It won't be very high. Anyway, output impedance will still be low. This is another circuit, a variant of the first circuit. I told you, if you want the output to rectify in the negative half cycles, the output should follow the input. You just had to change the diode. Here we had connected the diode in this direction. Here we have changed it in the opposite. So this is the waveform you are getting. And what would be the transfer characteristics for this? Negative input, negative output. So which quadrant you will get? Quickly you should tell me. When input is positive, when Vi is positive, no output. Vi is positive, then no output. When Vi is negative, I am getting negative output, which means which quadrant? Negative Vi is here. Negative V0 is here. So you will be getting it in the third quadrant. Negative input, negative output. This is the transfer characteristics for this circuit. You should be able to draw the circuit when you are given transfer characteristics also. That would be a great advantage, especially in the lab. If you are given transfer characteristics, you should be able to draw the circuit and do it. Okay, I hope you followed all these things. Now let's move on to a full wave precision rectifier. So since I'm not interested only in rectifying half signals, say I want a circuit which would convert any input signal, a sinusoidal input, to a full rectified output. We know how a full rectified, both positive and negative half cycles should be converted to one side. Say I want both of them to be converted to the positive side, then this is possible using a full wave precision rectifier. This is your Vi and V0 for a full wave. Actually, full wave is not for theory, not in theory syllabus, but is there in the lab. All of you would have already done it in the lab. Yes or no? You would have done the simulation of precision rectifier in the lab. It is there for simulation in the lab, not for discrete connections, but for simulation. So we have to understand the working of a full wave precision rectifier before we move on. So let me show you the circuit of a simple full wave precision rectifier here. This will be helpful in understanding the behavior. See, the VI is connected at this point. I am using all equal resistors because I don't want any gain in this circuit. I just want full wave rectification. But it is possible for us to do so many variants. I can have a different gain for one half cycle. I can have a different gain for another half cycle. All that I'll tell you in the end, just the variants. But we need to understand how we can get full wave rectification. For that, I need to use two op amps. As you can see, we are using two op amps, and you can see how we have connected diodes D1 and D2. This is a simple case where we have connected two diodes D1 and D2 as shown, and we have resistors like this. So if you observe, this second part is just a what? Input resistor R1 is R and feedback resistor is RF. This is a simple inverting amplifier. And this first part is your half wave precision rectifier. So it is like we are combining a half wave precision rectifier with an inverting amplifier to give total full wave precision rectification. If I want a full wave precision rectification, I'll do with a combination of half-wave precision rectifier, and output of that is given to an inverting amplifier. Okay, as simple as that. Now, let's try to analyze the working of this circuit. So, let me try to discuss the working. What happens? Let me say when Vi is positive greater than 0, positive half cycle. As soon as I write like this, Vi is greater than 0, it means it is going in its positive half cycle. Okay, please understand that. So whenever Vi is more than 0, it is increasing in its positive half cycle. What will happen? Which diode will conduct and which will not conduct? You see there is a positive voltage given at the inverting terminal. Output of the op amp, this VOA, the output of op amp A1, will tend to become negative. Yes or no? It will try to go towards minus VSAT. Because we have given a positive input, the output of the op amp will automatically try to move towards its negative saturation. But when it goes to negative saturation, you will see diode D1 will conduct because cathode of this diode is connected. So this diode conducts, and what happens to D2? Negative is connected to the anode, so this diode is off. So what will happen? D1 is on and D2 is off. What would be the equivalent circuit now? When diode D1 is on, you will see I have Vi through R here, and this R will be shorted to the output. You see R shorted to the output because this diode D1 is on. And since D2 is off, this R will be going to the next stage. Or I can almost say this would, what would happen here? There is an open circuit here, so there won't be any connection from this part here. If this was closed, then the connection would be. That's why you see this part, there is no connection because there won't be any current flowing now because of the open circuit in this. So the equivalent circuit now looks like this. I have an inverting amplifier. So if you give plus Vi, I'm going to get what? minus Vi here. It will invert it once. Minus R by R into Vi, I'll get minus Vi. And if I give minus Vi here, what will I get at the final output? The second circuit is also an inverting stage. You see, I've just written this R down here. This R and R, I already told you it's an inverting amplifier. So this minus Vi gets inverted again and I will have plus Vi. So what will happen to the final output? Output follows the input. Output now becomes equal to plus Vi whenever the input is also plus Vi, even when it passes through both stages, because the diodes are conducting in this fashion. Okay. So similar to that, we can see quickly what will happen when we are in the negative half cycle. When Vi is in the negative half cycle less than 0, you see the second diode should switch on. Naturally, you can understand if there is a negative voltage here, whenever there is a negative voltage here, this VOA tends towards plus Vsat. When it tends towards plus Vsat, this is positive. So diode D2 is on and this will be off. When D2 is on, what would happen to the equivalent circuit? And when D1 is off, how will it look? See, D2 is on means this connection is there. D1 is off, this connection is removed. Okay. And you have this resistance here. You have this R in series with this R because this connection is not there. Now, these two resistors are in series and it's equal to a value 2R. As you can see here, 2R. The input is there, Vi at this point through the resistance R, and this part is there as usual. So this would be the equivalent circuit of the op-amp. Now, if I consider node A and if I apply KCL at node A, in this circuit, if I apply KCL at node A, remember, since this is actual ground, the non-inverting terminal, this will be at virtual ground at zero potential. So the current through this resistor R will be Vi divided by R. Okay. The current through this first resistor is Vi by R. It will be entering this node, and the current through this resistor will be, if I consider this voltage as V, it will be V minus 0. The voltage here is 0, remember, because it is virtual ground. So the current through this resistor will be V minus 0 by 2R, or V by 2R in this direction. It is also entering. And what is the current in this? The third value, the third branch here is this resistor. The voltage here is also V. If this voltage is at V, because of the principle of virtual short, this should also be at V. It is understood. So V minus 0 by R again, which will be V by R. I hope you are following this. There are three currents and all currents are entering this node A. One is the input current Vi by R, because this voltage is at zero potential as it is the virtual ground. The actual ground is the non-inverting terminal. This is virtual ground. So you will observe, you will be able to reduce the equation using this, and you will get the value of V here as minus 2 by 3 Vi. And if I just proceed to the final equivalent circuit, this stage, the second stage with 2R here, and since this is ground, virtual ground, I'll connect it to ground here. R is here and the voltage V is input to the non-inverting terminal. This V value is minus 2 by 3 Vi. So this circuit now behaves like a non-inverting amplifier whose output voltage is 1 plus Rf by Ri, or R by 2R. As you can see, this is Rf and this is R1. So Rf by R1 becomes 1 plus R by 2R, which is the gain of the non-inverting amplifier, into the input voltage minus 2 by 3 Vi. If you simplify this, you will get the output still equals to Vi. So have we achieved the required condition? When the input was in its positive half cycle, we showed output follows the input, or V naught will be plus Vi. And when input is in negative half cycle also, we are able to show output will be equal to Vi only. So I am able to get the full wave rectification in this circuit. Okay. So this is a simple full wave rectifier. And if you try to draw the transfer characteristics, it would look like this. For positive Vi also, I am going to get positive output. For negative Vi also, I'm going to get positive output. So I will have two straight lines with slope 1 here. If this slope represents the gain, if I want a different slope, then I should use different resistors here and I should be able to change the gain. As simple as that. So if I want a value like this, say if I want this gain to be 5, this gain to be just 3, something like that, you can get such variables by changing resistors in the circuit. Anyway, let's not go about this design because as I told you, this is needed only for your lab. And I think if you do this full wave precision rectifier with gain 1, it would be sufficient. Consider all resistors to be equal. Okay. And if time permits in the end, I'll give this design in the notes. If you are interested, you can read through the notes where we can design for different slopes. And that means the output will be something like this. Positive half cycle, I'll have gain as 5. Negative half cycle, I'll have gain as 3. So you can get such variable voltages. You can play with the circuit well. So this is about the full wave precision rectifier. I think with this we'll stop today's class.